Yes.
What would lambda be if x is 2 and y is 2? Well, you'd have to go solve for it. Take your original equation, either 1 or 2, and replace the x and the y with 2. What would you get? 2e to the 4th equals 3 times 2 squared is 4, right? So 12 lambda. So divide both sides by 12 and you get e to the 4th over 6. Ooh, not a nice number, but it's lambda. It doesn't matter. That's the lambda that corresponds to the critical point 2, 2. Have we exhausted all of the ideas here? We said x couldn't be 0 and y couldn't be 0, right? Don't we need to look at that? Can we let x be 0 and y be 0? Let's see. Suppose x is 0. This is my second idea here. Suppose x is 0. Are we going to have any problems?
Yes.
What problems are you going to have?
On the first equation, you have.
On the first equation, if x is 0, this side's 0, right?
Yep.
That means the other side has to be equal to 0. So what would that mean?
Y is going to be equal to 0.
That would force y to be 0. Do you all agree with that? So suppose x is 0. Equation 1 would then tell us that y e to the xy must be 0. Oh, by the way, that's a 0, right?
Yeah.
So this is really a 1.
Yeah.
So that really just means that y is 0. All right, so x and y are 0. Big deal.
You have to go into the third equation.
Then when you go to the third equation, you're going to have 0 plus 0 equals 16, which isn't true. So far, this is all OK. It's when we get to equation 3 that we realize that 0 plus 0 would equal 13, and that doesn't happen, which means that we can't let x be 0.
16.
Yeah, 16. Am I thinking of the previous problem? All right. So if we assume x is 0, it forces y to be 0. And if they're both 0, the last equation is not satisfied. What if we let y be 0?
Same thing.
From equation 2, that'll force x to be 0. And once they're both 0, it's over. So we're done. Understand? So I hate grading these, but I take off points even if you have the correct critical points, if you have not entertained the different logical things that could happen. So like if you did all this and you got these two answers, but you never went and actually somehow showed proof that you thought about x and y both being 0 and drew the conclusion, then that's incorrect. Yes?
How do you know if that's maximum or minimum?
Oh, we just have to plug it in, right? Oh, no, that's a great question. This is a great question. There's only one point, right?
Yeah.
So is it a max or a min? I'm so glad you asked that question because I would have completely forgot to mention that. F22. So you plug it in, you get what? E to the 4th? So is that a max or a min? So how could you test any other point? Now, when you test another point, it can't just be some random point. It has to come off your constraint. So can you give me another point that satisfies this equation?
-2? No.
Any point that satisfies that equation. Yeah, how about this? The cube root of 16, 0. Doesn't that live there?
Yeah.
Okay, this point right here, or this number, 0. So if I take that, plug it in right there, I cube it, I get 16. All right, let's plug this into the function. What do you get when you plug that into the function? E to the 0, right?
Yeah, you get 1.
E to the 0 is 1. Which one of these is bigger? E to the 4th. So what we have is that this can't be the smallest number because there's one smaller, right? This is a maximum. Thank you for asking that question. So this is a max. The maximum value of that function is e to the 4th power. It happens at the point 2, 2. All right. Do you see why I didn't put this on the test? Okay. You could have just done 2 problems. So here's the function. This is e to the xy right there. And if I restrict it to just that, oh. There's that curve right here is the blue curve on the ground. Just those points. Here's the ground. Just those points plugged into the surface, and you get that curve right there. Come on, man. So we found the maximum point, e to the 4th. All right, the next one, let me just see what the work is for this one. Let's do it. I don't want to sell y'all short here. All right, let's at least set it up. What is the first equation going to be? Partial of this with respect to x. Negative 1 over x squared. Remember, 1 over x is really x to the negative 1, right? So when you take derivative of that, negative x to negative 2, and then you drop it down. So that's your derivative with respect to x. Equals lambda. What's the derivative of that with respect to x? Negative 2x to the negative 3. So you drop it down, you get negative 2 over x cubed. Yeah or no? Yeah. Okay, that's our first equation. I'll clean it up in a minute. What's our second equation? Negative 1 over y squared equals lambda negative 2 over y cubed. So those look very much the same. And then my third equation is the constraint, right? The constraint is 1 over x squared plus 1 over y squared equals 1. Definitely not a circle. Let's try and clean that first one up. I have negatives on both sides, right? So I can just multiply both sides by negative 1. I'm also going to clear the fractions. I'm going to multiply both sides by x cubed on that first equation. That's assuming, though, x can't be 0, but it's not in the domain of the original function. So I don't even care. I'm doing it with free will, okay? I don't even have to worry about it. Understand? That didn't happen in previous problems. I can multiply right now by 0. I can multiply both sides by x cubed without worrying about x ever being 0. So this equation, if I multiply both sides by negative 1 and then by x cubed, I get x is equal to 2 lambda. Right?
Yes.
X cubed here, x cubed here. And the negatives. Can I do the same thing with this? Can I multiply both sides by y cubed?
Yes.
Yes?
Negative y.
Because I don't have to worry about y being 0. So I'm going to, or negative y cubed. So I'm going to get y equals what?
Y equals
2 lambda again. I can set them equal to each other.
And x is going to equal to y.
And then x would be equal to y. Right? So I'm pretty much only going to have one thought in this one. Okay? It's going to be that x equals 2 lambda and y equals 2 lambda, which means that they're equal to each other. And once they're equal to each other, what can equation 3 tell me? 1 over x squared plus 1 over x squared again equals 1. I can replace y with x, or I could replace x with y, either way. I'm not working under any conditions here, am I? I'm not like, oh, lambda can't be this or x can't. I'm just like going at it. Put those together. 2 over x squared is 1. Multiply both sides by x squared. Oh, wait, you have to worry about 0? No, we don't, right? So multiply both sides by x squared. 2 is x squared. So x is what? Plus or minus root 2. All right. I think I'm ready to write down some points. I have that x can be root 2 or negative root 2. What will the y be? Root 2 and then negative root 2, right? Because x has to be equal to y. That's this right here. And what about lambda? It would, if you solve this for lambda, right, you just divide by 2. Whatever the x coordinate is, divide by 2, or whatever the y coordinate is, divide by 2. So it's just root 2 over 2, root 2 over 2, negative. And that's it. There's nothing else to go through because, I mean, this just almost fell completely out, like right into our laps, didn't it? It looked bad, didn't it?
I think you showed us the first one.
All right, now you plug those in, and is it easy to tell which is the max and min? Yeah, because these are positive numbers, right? So when we plug that in, you're going to get positive, positive. You put that all together, you get positive. So that's fine. And then you plug these in, you're going to get negative numbers here. So you put those together, negative. You would have to find the value, but I can tell you right now that's a max and that's a min. I don't know what they are, but.
So you really don't have to solve for lambda on this one?
You don't have to solve for lambda, no. You never really do have to solve for lambda.
It's just a scalar.
Yeah, because it's not going to be used to help find the max and min. The only thing finding lambda helps you do is keep track of your different scenarios. Because if you don't get what lambda is, but then later on you're saying, well, what if x was this and that, and then you realize, wait a minute, lambda is 2, but you already did that. You don't need to go through all that work again. All right, that one was actually not so bad, huh? It seems like that would be hard, like that problem would be difficult. You're taking this crazy surface and you're restricting it to that domain, which draws those curves on your function. See those black curves on there? And you were able to figure out where you have a max and min on there. It's crazy. All right, so what if you have a function of 3 variables? So now we have a function f of x, y, z. Well, there's good news. It's exactly the same. You're going to set the gradient of f equal to lambda times the gradient of g. You're also going to use the constraint equation. Notice that the constraint equation now has 3 variables in it, x, y, and z. So everything's pretty much the same, right?
Would that extra variable add an additional equation?
That's right. So I was just about to ask, but how does it change things? When you do this gradient, you're going to have 3 components to that vector. And when you do this gradient, you're going to have 3 components. So you're actually going to get 3 equations just from the first part, and then you're going to have a 4th equation. So you're going to be solving a system of 4 equations and 4 unknowns, and they're nonlinear. So here are your 4 equations. Partial with respect to f together, y and z, and then your constraint. Don't forget the lambda. Yeah? Hold on a second. Let's at least feel like we got somewhere today. Let's, not the cone. I don't want to do the cone yet. The cone is still a tough problem. It's still tough because of the shape of the cone. If it's a cylinder, it's a lot easier. All right, let's do this. Okay, we had a problem that we were working on that had, we were trying to find 3 positive numbers that added up to be 100 and multiplied to be the maximum it could be, right? So we wanted the product, we called it product. It was equal to the 3 numbers multiplied, right? But what would our constraint be? It can't just be any numbers. We have to be able to say that x plus y plus z equals 100. Then could I look at this product function p as p of x, y, z? In other words, a function of 3 variables. Yeah? We have a function of 3 variables, the product of the 3 numbers. We have a constraint that those 3 numbers have to add up to be 100. Right? So this is like your f, this is your g on the left side, and then we can set up our 4 equations. Yeah? What would equation 1 be? Equation 1 would be the partial of this with respect to x, which would be yz, equals lambda times partial of this with respect to x, 1. And when I say this, I mean the left side. That's your g of x, y, z. Okay, that's equation 1. What would equation 2 be? xz must equal lambda. Okay, what would equation 3 be? yx or xy equals lambda. What would equation 4 be? The constraint. X plus y plus z equals 100. Now what? You can set them all equal to each other. Yep, you can set them all equal to each other now, if you wanted to. But do you all understand the setup? Any questions on the setup? Now, let's eliminate some things here. These have to be positive numbers, right? Would it make any sense to consider one of them being 0? No, because we were trying to find the maximum product, aren't we? If we let any one of these be 0, you're going to get a product of 0, which is definitely not the biggest you're going to get, right?
Yeah.
Okay, so let's throw out the possibility that x, y, or z could be 0. So I'm just going to put here x, y, and z are greater than 0. All of them are greater than 0, strictly. Now they said it in the problem they were positive numbers. But just to be clear, it means it can't be 0. So let's start out. My first thinking here is that I'm going to let equation 1 equal equation 2. So yz equals xz, right? Now, what does that tell me? Y has to be equal to x. I can divide both sides by z. Why can I do it now? Because z is not 0. So y is x. Okay, great. If y is x, by the way, this was equation 1 being set equal to equation 2. So now what can I do? Say again? X.
She's putting it in
What equation are you working with?
3.
So in equation 3, what do you want me to do?
Put it to square.
Make this x squared. You could say x times y is lambda, but that would mean x squared equals lambda. I agree with that. Not disagreeing, but I'm not quite sure how that's going to help us.
Could you put equation 2 and 3 together?
Yeah, what happens if we set equation 2 and 3 together? So right now, I know that equation 1 and equation 2 have to be equal, which means that y has to be x. And of course, we also found out that x squared is lambda. But if I now take equation 2 and set it equal to equation 3, then I find out that xz must be xy, which means that z is equal to y. But what's y? Y is x.
So they're all 3.
So all 3 of them have to be the same, right?
3x equals.
Understand this? So this says that the x and y coordinates have to be the same, or x and y have to be the same. This says y and z have to be the same. Therefore, 3 dots means therefore. Therefore, x has to be equal to y has to be equal to z. They're all equal to each other in order for this to be satisfied. So what I'm going to do is I'm going to go to equation 4 now.
Just pick a variable.
I'm just going to pick one of them. It doesn't matter which one I pick. Equation 4 is going to become x plus x equals 100, which means 3x is 100, which means x is equal to 100 over 3, right? 100 thirds. So x is 100 over 3. And what's y? 100 over 3. And z? 100 over 3. Have I exhausted all the possibilities? I used all the equations, didn't I? I mean, there's nothing more. They're all equal to each other. I set them equal to each other. There's nothing I could do to like factor something out, right? So this is it. We're done. How do we know it's maximum? We just compare any other numbers that satisfy that. So here's my result. My result is that x equals y equals z equals 100 over 3. What is the product? What is the product of that? 100 over 3 times 100 over 3 times 100 over 3. Oh, I'm going to leave it as a decimal, but you can give me that in a second. This is 1, 2, 3, 4, 5, 6 over 27. What is it? Yeah, decimal.
The product 37,037.037.
037 point something.
037 repeating.
Okay. Approximately 37,037. That's what?
You're multiplying.
Yeah, that is a multiplication. Just seeing if y'all were paying attention. All right, so those three numbers add up to be 100, and they multiply to be about 37,000. And there's no other numbers that you're going to be able to find that are positive that can do the same thing better than that, or to get a bigger number. Now, to verify it's a maximum, what could I do, though, to verify it? Pick something, right? Give me something I could pick to test. Well, we're saying they're not 0, though, right? So I could do like 198, right? These add up to be 100. And when you plug them into our product, what do we get? 98. It's smaller than that, so that had to be a maximum. Understand? All right, that's kind of cool. See, did that problem seem pretty easy that way, or no? Let's do this one. Does anybody remember something like this from Cal 1? Cal 1? Yeah, it's an optimization problem. You're trying to find the maximum volume of a rectangular box with no lid if it is to be made from 12 square meters of cardboard. What are its dimensions? So I'll put the picture of what's happening here up, and then you have some cardboard, right? And what you're going to do is you're going to cut out the edges. No, wait, hold on.
Yeah.
Hold on a second. Find the maximum rectangular box with no lid. No, hold on. Let's not draw this picture yet. Hold on. Let's draw a rectangular box with no lid. Okay, that's a rectangular box with no lid. Do you all see it? Find the maximum volume of this. So let's try and talk about the function we're going to be trying to find the maximum of, which would be volume, right? We want to know what that is. Well, the volume of any box is what? Length times width times height. So why don't we go x, y, and z? Call that x, y, z? So we say x, y, and z. That is a function of three variables now, right? Do you have any constraints on those variables? Your surface area must be what? 12 meters squared, right? Now let's talk surface area. You have the front of this box, which is what? X times z, right? This is xz. And then we have another one on the back side, don't we? So 2xz. So this is my constraint. My constraint is that 2xz plus, yeah, now we need the sides. Sorry about that. This side is yz, but then we have another one on that side. So 2yz.
Would you include the one on the bottom?
I'm going to. I'm at 2yz. And then we have the last one, which you were saying was on the bottom. The bottom is xy. And there's just one of them because it's no lid on top, right? xy equals 12. That's it. Function we're trying to find the maximum of, constraint. 3 variables, right? Constraint equation has 3 variables. By the way, this right here, we have a technical name for the function we're trying to find the maximum of. This is called the objective function. That's your objective function. That's the one you're trying to figure out either the highest or lowest point. All right, so what am I going to do? I think I have enough time.
Find the partials.
Okay, so how many equations should I have?
4.
I should have 4. What's equation 1?
YZ
Yz equals lambda times.
2Z.
Now this is going to be a little different, so let's check this out. Partial of this with respect to x is 2z plus y. All right, that's a little different looking, isn't it? Equation 2. Partial of this with respect to y, which is xz, equals lambda 2z plus x. And then third equation, xy equals 2x plus 2y. Oops, I forgot my lambda. Lambda 2x plus 2y. You all follow that? Any questions on that? Fourth equation is my constraint, right? 2xz plus 2yz plus xy equals 12. Excellent. What would you like to do with that? Can you make equations 1, 2, and 3 all look the same? The left sides. I can multiply the first equation by x, the second equation by y, the third equation by z, and they'll all be x, y, z, x, y, z, x, y, z, right? Then I can start setting them equal to each other. Now, am I allowed to do that? Do I need to be fearful of, oh, well, x can't be 0, y can't be 0, z can't be 0?
Yes.
Should I be fearful?
Yes.
Should?
Not really, because we're making a box.
Yeah, we're making a box, right? So in real world here, I'm not going to sit here. I can't make, if I let x, y, or z be 0, my volume is going to be 0. And you can't use 12 square meters of cardboard if you have a 0 volume container. Unless you have a Klein bottle. You don't know what a Klein bottle is? It's a container that has 0 volume. Okay, that's not for here. It's not for today. All right, so let's multiply both sides by x here. We get x, y, z, and I don't have to worry about it, equals lambda. Let's distribute the x through the parentheses. 2xz plus y, x, plus xy. I decided to just pass the x through the parentheses part instead of out in front of, with lambda. That fair? Next equation. xyz equals lambda, then what?
Distribute 2y
2yz
plus
plus xy, and then my last equation, xyz equals lambda. I'm multiplying both sides by z, 2zx plus 2zy. I'm putting them in alphabetical order, but same thing, right? Multiplication doesn't matter. All right, so that is a fair algebraic move. I have not made any additional restrictions on my equations. All right? All right. I say we start setting them equal to each other and see what happens. Hope for the best. Let's take equation 1 and 2 to set them equal. And when I do that, I get lambda 2x. You know what? Let's distribute the lambda through. Can I distribute the lambda through this? Is that all right? I get 2xz lambda plus xy lambda equals what? 2yz lambda plus xy lambda. Ooh.
You move everything to the left side.
Move everything to the left side. Do y'all see what happens?
Yeah, the xy.
The xy lambdas cancel, don't they?
Yes.
And you're left with 2xz lambda minus 2yz lambda equals 0.
Can you factor out 2?
Yes, you can factor out a 2 and a lambda
And the z.
and a z. So if we pull out a 2z lambda, we're left with x minus y, right? Equals 0. And what does this tell me?
X is equal to y.
Either z is equal to 0, which can't be, right? Because we're not letting z be 0. We'll have no volume. Lambda 0. Should I consider lambda being 0? No, because if lambda is 0, what's your first equation say? Y times z has to be 0, and that means one of them had to be 0, so that we're throwing that out. So these two scenarios I don't even have to worry about. This just really tells me that x is equal to y, right? X minus y has to be equal to 0, so x has to be equal to y. I wonder if something similar will happen if I do equation 2 and 3 together. Well, we need to work through it, okay? You all ready to set equation 2 to 3?
Equation 3 has a 2.
Yeah, it's not going to work. Is that what you're saying?
But you did multiply by 2.
Oh, did I forget to put a 2 here?
2 was.
Oh, yeah, I forgot to put a 2yz here. 2. All right. Well, shall we try 2 and 3 together? Yes? All right, so if we do 2 and 3 together, let's remember x has to be y, right? Right? That's okay. So let's set equation 2 and 3 together. Equation 2 to equation 3. Whoa. Wow, okay. Equation 2 to 3. I'm going to distribute through here. I'm going to have 2yz lambda plus xy lambda. That's equation 2 equals 2xz lambda plus 2yz lambda. So just distributed lambda through here, set them equal to each other. Do we get that same cancellation?
Yes, with 2zy lambda.
We do. We get this and this cancel, don't they? And you get xy lambda equals 2xz lambda.
So then you can factor out
Move everything to one side.
x lambda.
Factor out an x lambda. And you're left with y minus
2.
2z equals 0. Can't factor out the 2 that time. So can x be 0? No. Can lambda be 0? No. So this tells me that y has to be 2z. But isn't that the same as saying that x has to be 2z? Why? Because x and y are the same, right? Yes? All right.
So you can
Now
put
what?
it into the fourth equation.
Now I can go to my fourth equation. I can replace y with 2z, x with 2z, and replace z with nothing. Just leave z as z. And I'm going to have one equation with one variable, and I'm going to be able to solve for z, then come back and get xy. And we'll be done. It's almost fun. Equation 4. All right, 2xz plus 2yz plus xy equals 12. So this is 2 times x was 2z, times z, plus 2y, but y was 2z times z, and then plus x times y, which is 2z times 2z, equals 12. See, this is a good time to, strike your z's. If your z's look like your 2's, this would be pretty confusing if you couldn't distinguish the,
Yeah, you get
right.
12z squared
So what is this? This is 4z squared
plus 4z.
plus 4z squared plus 4z squared equals 12. Oh, how boring is this? 12z squared equals 12. So z is plus or minus 1, but I'm only going to consider a positive because, well, it's a box and I don't have a negative side on it. So z is 1. What if z is 1? What's x? 2, and what's y? 2. So there are the dimensions of the box. You need that box to have, yeah, now you could check to say that's a maximum. Two, 2, 1. What is the volume? 4, right? The volume of that box is 4. So that's the way you do it. What would happen if I would have had a lid on that? What do you think would have happened? It would have been a true box, right? It would have been all sides equal. But because we didn't have a lid on it, had to change it up a little bit. All right. Do y'all want to sign in, or
Yeah.
it's been a while? Let's see. That hadn't been. You signed in on the 9th, but then you took a test, right?
It's like
So today's the 18th.
9 days.
All right. Who always gets? You always have to wait back here, right? Y'all can sign in first. All right, we're done.